So welcome to this class of EI 331. In this class we'll study about the things which we have discussed in the last class. So moving on from the discussions which we have done in the last class. In this class we will discuss about some of the basic things about the VLSI and what sort of design matrices we should use to evaluate the design, and we'll also see that which are the various companies which are working in the field of VLSI and the basic design flow. So to start with, in this course basically what we are supposed to do is this integrated circuits which you can see here is what we have to design. So inside this chip, what we call as a chip, so this block which you can see here is the chip. So inside this IC which you see from the outside, you want to see that what is inside and how to design it. So that will be our aim in this course. And as you can see that the area which you can see here is very small. So the aim will be to design the whole circuit in this very small area. So that is what it means by saying that it is VLSI. So it is a very large scale integration. So too many number of transistors will be used, too many number of transistors are there in the very small area. So that is why it is called very large scale integration. And to evaluate the design, whether your design is a good design or not, so what we have to see is like we decide upon certain factors. They are like the speed of the circuit, that at what frequency this circuit is operating. Then we also see about the power consumption, then how much area that design is taking, and what is the yield of that design. That is like in that particular area how many number of ICs you can produce, how many good number of ICs we can produce. So that is what we have to see. So yield. So let's see, and we'll also see this VLSI components. So when we talk about the VLSI systems, so this VLSI systems consists of various components in it. So the basic component is obviously the transistors, because all the switching or all the circuits which you see are made by transistors only. So the transistors will form this basic component. But apart from the transistors are also of two types: NMOS transistors and PMOS transistors. So you can see the symbol of the NMOS transistor and the PMOS transistors as well. So NMOS stands for your transistors in which the majority charge carriers are electrons, whereas the PMOS transistors are the transistors which have holes as the majority charge carriers. So these transistors, as you can see in the symbol, so these are the symbols for your NMOS and PMOS, whereas the when we apply certain voltage, so the gate voltage controls the operation of the device. So in one condition the device will be off, whereas in the other condition the device will becomes on. Similarly for the PMOS as well, there is a slight difference between the symbol of NMOS and PMOS, so that you can see here that in case of PMOS there is a bubble. So in case of PMOS on the gate we use a bubble, whereas the symbol for NMOS is without bubble. Now in this circuit you can see that your transistors, your circuits are like, if you use transistors, so then by combining the transistors we make the what is called as a basic circuit. So this basic circuit is inverter. So this inverter which you can see in the there are two transistors which we use here, so a NMOS and a PMOS. So a NMOS is a transistor which is connected towards the ground, or the pull down network is a pull down network, whereas the PMOS is used in the pull up network. So the idea from this slide which you can take is the transistors are connected to form what is called as the inverter. So the basic building block of all the integrated or all the digital integrated circuits, or usually also the analog integrated circuits, are inverters as well. So transistors are used to make inverters, and then these inverters are connected back to back in cascade with each other with the help of certain wires. So these are the four like circuits you will get, but then the circuits are made up of various type of various inverters connected back to back, and these inverters are connected with wires in them. So there'll be wires, there'll be transistors. So these are the basic things which are there in the circuits you will find. Okay, so your whole circuits, whatever circuits we are going to study in this course, or if you think that the circuits are made made in this VLSI nowadays, so you see that they are made by CMOS circuits. So this is what you mean by CMOS circuits. Now, how does an IC look from look like? I mean, at the circuit level, we have seen in the last slide that how the things will look like. But at the physical level, if you just see at the physical level, at the wafer level, then you can see that the transistors on the wafer level, at the physical level, they will look something like this. So in the physical level, there will be in this diagram, if you'll see, so this diagram have like some transistors they are fabricated in this green layer. You will see, you can see these transistors are here. Then there will be this is like various layers are there. So at various layers you may see, because this is a multi-layered this multi-layer wafer fabrication. So in multi-layer at various levels we see transistors, whereas the transistors are like usually they are formed on the top, but when it is a multi-layer, then at first level we form the transistor, then we form again a substrate, then some more transistors. So similarly in this way the transistors are formed. Okay, then we also see that so this slide generally tells you that there'll be transistors and how the transistors and the wires will look at the physical level. And we also know that you might be knowing this, that the ICs were first, these transistors and ICs were first invented by these inventors Kilby and Noyce. Okay, so this is what, just to show you the historical background that who has developed these ICs for us. And then you may also have heard about in the VLSI this one law which is called as the Moore's law. So if you've not heard about it, this law is again plays important role in in guessing like how many number of transistors or what the scaling and how the scaling will look like in future years. So as per the Moore's law, the number of transistors which are integrated in a certain area, okay, becomes double every approximately 1.5 or 2 years. So this is what is called as Moore's law. And this Moore's law is why this Moore's law is important, because this Moore's law was predicted in year 1960 somewhere, and since then people are trying to prove that this particular law will not hold, because it is very difficult to integrate or to double the number of transistors in a certain area in every 1.5 or 2 years. So that feels like very difficult and impossible to achieve. But since 1960 till to 2020, it is almost 60 years, people are like somehow they are able to integrate the exactly, or not exactly if I say, almost twice the number of transistors as it was there in the last 1.5 year. So that means that the Moore's law still holds true. Okay, so this is what the importance of Moore's law in it. So the Moore's law is not a technical law as such, but it says it just provides you the guess of like a very rough guess, like how many number of transistors will be there after 2 years. Okay, so after every 2 years you can easily guess that how many number of transistors you will see in the upcoming ICs. Okay, so that is what the importance of this Moore's law is. And this is the person, this Gordon Moore, who is, this photograph you can see is Gordon Moore. So this law is given by Gordon Moore. Now you can see that considering this Moore's law, if I just show you evolution of this transistors, how these transistors have evolved since like 1970, when this law was like predicted in year 1960 somewhere. So after 1971, how the this fabrication took place, okay, or how the number of transistors count in an IC increased. So you can see that it is increasing linearly, okay, since I mean up to 2011. After 2011, I mean I was not able to, I mean I was not having that chart with me, but still the law is like holds true, and still the number of transistors are becoming like increasing day by day, and it is becoming like multiplying by a factor of 2 in every 2 years, okay. Then just to have like idea that when we talk about like how small the transistors are, so this 180 nanometer, if you just see the 180 nanometer, this diagram, so 180 nanometer was back in around somewhere 2002 or 2004. So the transistors on an IC were in this range, 180 nanometers, somewhere in that era, okay. So if you'll see the diameter of a human hair, then it is like somewhere 75 micrometer, and it looks like so large. So compared to that, if you just see 180 nanometer, then 180 nanometer is something like a dot, okay. So this much small area. So you can compare, like this diagram is just shown you to just compare, like how you can compare that compared to your human hair, how much smaller this 180 nanometer will look like, okay. So this is something like that. So you can compare it, that at what small level we are working, okay, and at what small level we are talking. So how difficult it will be to see the transistors and to fabricate them, that like manually. It is impossible nearly to fabricate the transistors manually. Everything we do is like automatized because of the this small size, okay. So to the emphasis of like why I have told you so many things is just to emphasize this particular point, that how small the transistors will be actually. Now let's see that if you just go for the microelectronics, if you just start like how important this VLSI is in the industry, and how it can be helpful in making your future as I mean how you can choose this VLSI to make your future career. So you can like work in the field of VLSI, and can work in the various domains like digital VLSI domain, analog VLSI design domain, and the mixed signal and design domain. So digital VLSI design domain, you easily know that you can easily identify that the circuits will have the digital functionality, okay. So the circuits will be digital circuits, whereas in the analog VLSI domain, we talk about the analog circuits, okay. The circuits which you have studied based on BJTs, and the circuits like amplifiers. So those circuits, oscillators, so these are the circuits which are analog circuits. You can make them as well. Digital circuits like gates, okay, counters, these are the circuits which are the digital circuits. So you can make them as well. And there are like certain applications which use mixed signal design. So mixed signal means the combination of digital and analog circuits. So in the same circuits, on the same IC, we make some digital components as well as some analog components. So this particular type of circuits are called mixed signal circuits. And along with this, you will also have the fabrication laboratories. So the fabrication laboratories, I mean the various the three domains which I have talked about, digital VLSI design, analog VLSI design, and the mixed signal VLSI design, they are the design. They are from the this is the classification from the design perspective. So people get the job in the design perspective as a design engineer in these domains. Apart from the design engineers, people are also able to fetch the design, the job as a fabrication in the fab labs as the fab engineer. So in the fab labs, what they do is whatever the design is provided, whether it is a digital design or analog design or a mixed signal design, if the fab has the facility to fabricate these circuits, then this fab engineers or the engineers working in the fabrication laboratories actually do the work of this fabrication, which is provided by the design engineers, okay. And along with that, people are working in the field academics. Also people are working in the VLSI domain, but apart from that, there are like some research institutes like as mentioned here, so you can like find the jobs in those field as well. So this is, I mean, people are also going for higher studies in this MS, PhD. So that is also applicable field. And this digital electronic, I mean, this integrated circuits, you may find them like everywhere. Okay, so almost everywhere this VLSI circuits, this integrated circuits are there, because whatever devices we are using, all the devices have the integrated circuits into them, whether it is computers, it is mobiles, or your household devices, okay, satellites, robots, or some this cars. So all this have this digital this integrated circuits into them, whether it is a digital integrated circuits or the analog integrated circuits. Mostly you will see digital integrated circuits into them, but in some applications analog integrated circuits are also used. Okay. Now this is a small list of the companies which are working in the field of the semiconductor industry. It's not an exhaustive list, but it is just showing you some of the important this companies which are working basically in the field of VLSI. So the objective of this, the aim of this particular lecture is to just show you that what are the perspective in which, I mean, what are the perspectives where you can explore VLSI and how it is useful in our daily life. Okay, so that is what I just want to emphasize, and connected to that only I want to show you that where you can get the job as well, because as in student our aim is like to get a good job as also. So these are the various industries, I mean, these are the various, in this particular semiconductor or the chip industry, you will see these are the important companies which are working. Okay, and these are all well known companies. So if you are like if you are absorbed in particularly any of these companies, the package is also very good. It's, not very good, it is a very high package. Okay, and it is very difficult to get in, to enter into these companies as well. It is not so easy. Okay, so these are very well-known companies like Intel, Samsung, Toshiba, then Sony, then AMD. Okay, so many of these companies you may be you might have heard about them as well. Okay, so Nvidia and this Broadcom, okay, Qualcomm, so Mitsubishi, okay, and Mitsushita. So okay, so these are like these are the various important companies. Okay, some of the important companies which you can see here. Okay, and these are working in the various countries as well. Okay, so some of the countries are like US, China, okay, then Japan, Taiwan. So these are the important various countries which are dominating in the field of VLSI. So India is also planning to do it uh, presently. So you will see that India is also coming up with this particular uh, proposal for the industry, that if they install it here in the India, then they will get some production linked incentives or the design linked incentives connected to that, connected to this design, because uh, we want our, I mean, our leadership wants country to be independent in this field as well. The desire is that, but it is not so easy. It requires a lot of financial support as well. Okay, so installing a fabrication laboratory is itself a huge, it takes a huge cost, so billions of dollars, so 20 to 30 billions of dollars is required. So that government or a big industrial groups can only provide. So it is little bit difficult, but we are trying, and like if you try something, it's like then only you can achieve something. So that is what the thing is. So in the previous slide, if you just see, so I mean, there are like, I've just classified them, that in USA there are almost total 16 almost number of foundry centers, and in Japan. So the importance of this slide is which are the countries which are working in this IC field. So if you just want to think in this field, then you should know that in which countries you will get the job. Okay, so these are USA, this is like USA, Japan, Taiwan, as we have already seen, Singapore, Korea, and some of the Eastern or Western European countries, and Israel is also a very dominating country in this field. Okay, so this was all about, in short, that which industries. I mean, if you just select this industry, so which particular countries are working in this field, and what are the various levels which you can think. Okay, but if you just see that how this design takes place, so just to show you a crude idea, just to get a crude idea that how the I mean, how you get an IC. Okay, so what happens? So initially what happens is, if we just talk about the, suppose we have the this what we call as the substrates we have, let's say, and if we just want to design a circuit, or want to implement want to make a new integrated circuit, so in that case what we do? So the idea is something like, if we I mean, some person will have some idea. Okay, let's say some person is coming up with a new idea. Let's say making something which can I mean, it's a very common idea, but I'm just telling you, just because you can have the understanding of this. So some person may come up with a particular idea. Let's say I want to design uh, 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 a machine which can cut the grass in the garden, let's say. Okay, and it should be automatic controller. Okay, or you can come up with a sort of automatic mop. Okay, so you want to program it. Okay, so automatic, like, no, to clean the houses you want the mopping device. So what you will do, that this is the basic idea, let's say. So for this you will write certain you will find that let's say my machine should be of this much area, it should, like, it should be battery operated, and then it should work at this much power, then it should operate for this many hours, let's say, and it should be able to no, automatically differentiate between the walls and the furniture which is kept there. So it should not collide with that furniture or the walls. Okay, so like this you come with some certain specifications. So my machine should be able to do this particular thing. Let's say if I talk about automatic or electronic mop, which is like, which will automatically if you just press, you have to just press a button and program it, so it will clean your house, let's say, of 1000 square feet or whatever. So that is what my idea is, and then accordingly I will write certain specification, that my machine size should be how much, and what sort of things it should be able to do. So I have given you certain examples of some of the things that what I want. Okay, so based on this, then I will write a certain I want a certain hardware to do these all things, certain IC. So what I will do, I will design the system accordingly, because I want that this particular some of these circuits, like some AND gates will be working, okay, some NAND gates will be working in that. Okay, or some combinations of some circuits. Sometimes I have to like bypass some certain circuit, or I have to, like, operate multiple gates simultaneously. So something I have to do in between. So the idea is, I have to design a system accordingly, and then once the system is designed to get that particular to get that particular idea working. Okay, so then we analyze the whether it is working properly or not. If it is working properly, then we go for the fabrication step. If it is not working properly, then we again, from step 4, we go back again to the step 3 or step 2, and we check whether our specifications are right, or is there any fault at the design system level. So something we have to correct in that. So if some corrections are required, then after that correction, we again come back to the step 4, and we try to model the system. Okay, until and unless it is not working satisfactory, we move on to the step 5 from step 4, only if the system, whatever is desired by us, as an engineer, or from our client. If some client comes up with a certain idea to a design engineer, and wants this particular idea to implement, so he has to, like, backtest the things multiple times. If the things are working, I mean, until and unless the things are not working properly at the circuit level, at the simulation level, then at the testing level, then up till that time, we have to, like, keep doing those things. Once it is satisfactory at that level, then only we go for the fabrication. Okay, and once the circuit is fabricated, then this IC, you can see here in the at the step 5, that some IC is fabricated. Then once the IC is fabricated, then again we have to check this IC whether after fabrication, because at the simulation level, let's say the IC was working, but when you fabricate the ICs, sometimes the IC does not work after fabrication, does not work properly after fabrication, though it was working properly before fabrication, but it does not work properly after fabrication. So in that case, what we have to do, we have to, like, again test it. If the IC is not working properly, again we have to go to the step 4, and this IC, what we have already fabricated, will be discarded, and we have to, like, modify it again, and then once it is satisfactory at that level, then we go to the step 5 again and step 6 again. So these are like repetitive things. Okay, it is nearly impossible to do the design in linear way. Okay, one step after the other. Continuously you have to like backtest your model or whatever the system you have made until and unless it is not working satisfactorily. So this is what the basic your design, what is the work of the design engineer is. Okay, so how you design a system. And as you can see that this system what we have designed is what we have seen is not a completely new system. Okay, this is the system which we follow for any engineering design, whether it is IC design or any machine design or like any component design, any electronic circuit design. We follow the same thing until and unless the circuit is not working properly, then we have to like continuously backtest it. Okay, we go for the commercial fabrication or commercial implementation of the circuit only when the circuit is working properly at all the levels, not only at the simulation level but at the physical level as well. Okay, so this is what about. So you can see here, in a short diagram that how your ICs are looks like. Okay, in the modern ICs, if you'll see, they are of multiple types depending upon how they are packaged. So this is one of the type. Okay, so whatever we have discussed in the last slide, this is again that in the detail, but I have already explained you the things there itself, so no need to go in these things. But this is like some idea you have that is not shown correctly. I should have used some other slide, but I just wanted to convey the things and I have conveyed it in the last slide. And then from the specifications, again the same things. You have some specifications, then based on that you write some instruction set, and then you have certain circuits, so there will be some interfacing pins, input output pins. So that is what you do, and then you write a sort of a program. So this program is not, it is not written here to read it. Okay, just it is shown that there will be some algorithm which you make. Okay, it's not a sort of program, it is just a sort of flowchart or a sort of algorithm. So from that algorithm there are multiple connections which go from which there are this just to convey that it is a continuously backtesting stage what you have to do. So until and unless whatever functionality is desired that is not satisfactorily implementable, till the things you have to design the things. So this is what the design part comes. So first you write the code. Okay, whether if it is a digital thing, then you can, there are multiple ways to write, to implement these circuits or to simulate these circuits, I should say. So if it is a very big circuit, then we go for what is called as various languages, sort of. Okay, various hardware descriptive languages, and one of this hardware descriptive language or which is usually used in the industry is VHDL and Verilog. VHDL stands for Very High Speed Integrated Circuits Hardware Descriptive Language. So V is for VLSI, let's say very hard VLSI, VHDL. Okay, so HDL is the common word. So HDL is Hardware Descriptive Language. For what? Very large scale integrated circuit. So V stands for that VLSI. Okay, so VHDL, and then there is equivalent to that or like somewhat modified form of that. Other languages there, other hardware descriptive languages also available. That is Verilog. So these languages are VHDL and Verilog. Verilog are basically used to write the, whatever, let's say suppose you want to implement a circuit in which there are multiple gates, as you can see in this diagram. Okay, so what we do, rather than just putting the gates, we write a code. Okay, as I was telling you that if the circuit is too big, if you just drag and drop the components, then it will be like at the circuit level you may find it very difficult if the number of gates which you are using are too many. So you may miss some connections in between. So it is good to write the codes in that case. So if the circuits are smaller, then you have the choice either to write the code or you can drag and drop and make the circuits or simulate the circuits. But if the circuits are very big, okay, if you are making a certain microprocessor, then there will be too many gates which will be involved into it. So in that case, the people write codes for that in the hardware descriptive languages, and the languages which they use are usually VHDL and Verilog. There is some difference between VHDL and Verilog, and usually Verilog is used in the industry, okay, but they are somewhat similar as well. Okay, some differences are also there, some similarities are also there. And this is what about the digital integrated circuits, but in the domain of analog integrated circuits also there are like the descriptive languages, hardware descriptive languages also for the analog domain. But in this course we will concentrate usually on the digital aspect, so digital circuits. So I am just telling you about the digital, this particular showing you the how the design works in the digital domain. So we write certain code. So the point is just to show you that we have to write certain code. So once certain code is written, then that code will give you certain components, certain connections, certain connected gates. Okay. Then at the lower level, if you'll see, okay, from the means these gates are made by various transistors, right? So the device layout for the circuit will look something like this. And when you just simulate the circuit, you have to verify whether it is working properly or not. So then depending upon the design schematics, this is the design schematic you can see, then you just get the waveforms also whether it is working properly or not. So once it is like working properly, so I have shown you various levels that how the things will look like. Then you have this device transistors. So the circuit whatever you have written first code that have generated certain gates, so inside the gates there are certain transistors, so those gates are implemented with the help of transistors. Then to make these transistors, what we have to do is we have to make a layout. Okay, so there is a device layout, okay, that how which device will come where. Then this devices you have to connect with them. Okay, I mean you have to connect you have to connect one device with the other device as the wire. So this routing has to be done, okay, and they has to be like optimized. So these are the various levels, and after this doing this all, what we do is like we have a mask layout sort of thing. So this mask layout, whatever you have generated it after doing all these processes, this mask layout is sent to the fab labs. So the work of the design engineer is to do all this these steps. Okay, once this mask layout is generated, this mask layout is sent to the fabrication laboratory, and then the work of the fab engineer is to fabricate this particular mask. Okay, so they check it whether it is working properly or not. Once it is working properly, all the connections are there, all the transistors are as per the specifications which are available in the fab laboratory. So if they are like if they are within that range, then only they fabricate it, or else they will return the things, okay, back, and you have to like correct them and send it back to them. Okay, and this is all like in the soft copy, the soft format. So I've just tried to give you how in the VLSI industry people works. Okay, what levels they work, at what levels they work, and what is their work is. So I just tried to give you a preview of those things. And in the fabrication laboratory, this mask layout which you have received. So now the engineers, what they will do, they will write this mask, and then this mask is printed on the certain wafers, and when this wafer you will see that like there are many small areas. So each small area is called a die into it. Okay, so die. So this die will be fabricated in a circuit and in the chip, and then you get this particular integrated circuit. So this is like IC which you get. So the IC which you have seen there in the first slide, not in the first slide, there the first point, okay, the idea level. So that IC is like how this is made here. Okay, so these are the various steps which are involved in making an integrated circuit. Okay. Though the things are not very much clear at this level, but it is an introductory class, so I hope you may be able to understand the things. Then we test it after making the step 6 which I have shown you there. What we do here is once the IC is fabricated, then again we check it whether the for the functionality, and also not only just the functionality, but also for the power consumption, how much power it is consuming, how much delay it is producing. Okay, so functionality, so it should give. Okay, the functionality, if it is incorrect, then it is of no use. If the functionality is there, but still the power consumption is too high, or the signal delay is too much, okay, or the pins which you have desired as to behave like some in some manner, if they're not behaving at that in that way, then you have to redesign the things again. Okay, so this is what you have to evaluate the design, and if it is satisfactory at all the levels, then only you go for the commercial production, else you backtest it. I mean, you have to redesign the things, modify the things, and redesign the things. So that's what you keep on doing. So after all this discussion, you may be like, just try to classify that we have seen that what is the designs, what are the design steps to do the VLSI design. Now let's see that how we classify the various type of IC technologies. So the integrated circuit technologies are classified in certain ways depending upon which type of components which we are using to fabricate the ICs. So if you are using a BJT, then it is called a bipolar IC. If you are using CMOS, so then it is called a CMOS IC. If you are using a mix of bipolar and CMOS, then it is called a bi-CMOS IC. Okay. Similarly, there are other type of silicon on insulators. So what we do is we take an insulator, over that we use some semiconductor, so then it becomes a silicon on insulator. Okay. So the semiconductor which we are using here is a silicon basically. So silicon on insulator. So the classification of ICs are at this level also. Then there is silicon germanium type of IC. So this ICs are used for RF applications, whereas the another classification is for gallium arsenide circuits. So gallium arsenide circuits are for other high speed applications. Okay, germanium ICs are also used for high applications, whereas gallium arsenic ICs are also used for high speed applications. Okay, or for high frequency applications, I should say. So this is the classification of various IC technologies. And if we just consider about the CMOS digital integrated circuit. So earlier in the last slide we have seen about the various competitive technologies, or the logic families, I should say, not the logic families basically, but the various which type of transistors you are using to implement the things. So based on that, okay, or which type of material you are using to fabricate the things. So based on that, the classification was there. But if you just talk about the CMOS digital integrated circuits, then these digital integrated circuits can also be classified in certain ways as the static circuits and the dynamic circuits. Okay, so the static circuits are used basically for your implementation of combinational circuits, whereas the dynamic circuits are used not only for combinational circuits but also for the sequential circuits. Okay, so that is what the difference is. Now in the static circuits, you will see the classical CMOS, which we are going to concentrate in this course particularly. Okay, we will study somewhat about the transmission CMOS gates as well, and the CVSL gates. Okay, so the CVSL stands for cascode voltage switch logic. Okay, and these are the things which we are going to concentrate. And in the dynamic circuit, if you just classify, so it is like domino logic. So what is domino logic? If time will provide, I mean, if time is sufficient, then we will discuss those things as well. This domino logic, NOR logic, or the TSPC logic. Okay, so what are this? We'll discuss them in detail when the time will provide. So I hope for today, this particular introductory part is now over. In the next class, we'll start with a new topic. So this particular PPT is like over at this stage. So thank you for everyone. Thank you to everyone for listening. So thanks. I will meet in the next class then. Thank you.